Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to continue our discussion of enthalpy, specifically the relationship between enthalpy and internal energy under different physical states of matter. For example, what would the value of enthalpy be under solid, liquid, or gas, and what would the value of internal energy be under a physical state of solid, liquid, or gas. Next, we're going to look at the relationship between enthalpy and spontaneity of a specific chemical reaction, whether it's a physical change or a chemical change. And so I thought it would be appropriate to draw this cartoon of Q transforming into H. And so if you guys recall, Q is this notation that's used to represent heat in a calorimetry experiment. And since the calorimetry experiment that you guys typically perform in lab is a coffee cup calorimeter, it's under constant pressure. And so the value for Q turns into enthalpy, or H. So here you have kind of like this whole Superman effect going on, where you have Clark Kent with glasses and he comes out a superhero. All right, and so just to review some more items that I've kind of touched on in the previous lecture video, remember that enthalpy is a state function, and the differences between the state functions allows us to gain a better understanding of the thermodynamic process, all of these microtransactions in a chemical reaction that we can't really see, observe, or measure. And so by taking the difference of a state function, we can gain an overall understanding of what happened in that chemical reaction. All right, and so once again, I repeated it in my introduction of the cartoon. Enthalpy is heat, but it's measured under constant pressure. And so here in this case, constant pressure, heat under constant pressure is represented as Q sub P, and we're simply replacing that term with the letter H to represent enthalpy. Now, one way to define enthalpy is the overall change in internal energy plus pressure times a change in volume. And the units for enthalpy is typically expressed in joules, kilojoules, or joules per mole, or kilojoules per mole, depending on the problem, depending on what the question is asking, depending on the scenario. And so you guys have worked with enthalpy before in the first semester of general chemistry when you guys were learning about like Hess's law and all of that stuff. And so if the change in enthalpy is positive, right? So if you guys were to perform some kind of calculation and you notice that the final answer of enthalpy, or delta H, is positive, then it's representing an endothermic reaction, where overall heat, let me just black. There's an overall shift in the thermodynamic process such that heat is gained by the system. And so if your enthalpy is negative, that means that an exothermic reaction occurred. And so for an exothermic reaction, heat is being released by the system. So there's just a couple of items that I wanted to review for enthalpy that you guys might have been exposed to in the first semester of general chemistry, or some of the things I've discussed in the previous lecture video. So let's go ahead and talk about the enthalpy in the physical states of matter. So we know that there are 3 physical states of matter: solid, liquid, gas. We're not going to talk about plasma. So right now we're just keeping it to the 3 common physical states of matter. And so here for solids and liquids, if you guys think about the nature of, if you guys think about their definition, a solid has a fixed amount of volume and a fixed shape, right? So that's a definition from the very beginning of chemistry. For liquids, liquids have a fixed volume, but they have an indefinite shape. And so for this topic, we don't really care about the shape, we just care about the volume. And the reason why we care about the volume is because it's seen here in the equation. And so how does the different physical states of matter affect the change in volume, this specific term? And so for solids and liquids, the change in volume is very minimal, it's minuscule. So we can go ahead and approximate that value to 0. And so if I plug in 0 into delta V, it would make this whole term equal to 0. And so overall, for for enthalpy and the physical state of matter, solid and liquid, the enthalpy is equal to the internal energy. And so this is really cool because once you guys calculate enthalpy, you guys now have calculated the change in internal energy, and vice versa. So for solids and liquids, the change in enthalpy is equal to the change in internal energy. And so a lot of your chemical reactions are actually occurring in an aqueous state. And so that kind of falls under the subcategory of liquids. And so this is one of the reasons why we can attribute or express enthalpy as heat. And we know that enthalpy is heat measured under constant pressure, but this is further kind of like exacerbated that since there's typically a small change in volume, then we can say that the change in enthalpy is equal to, or approximately equal to, the change in internal energy. Now, if you guys have like this vigorous reaction where there's an overall net gain in volume, then obviously this statement does not apply. For gases, the change in volume does not equal to 0. And so if you guys think about like blowing up a balloon, right? And so if you increase the number of moles of gases inside that balloon, then you increase the volume of the system. And so since the change in the volume is not equal to 0, there is a significant change that is observed for delta V. And so when we're looking at the equation that relates enthalpy and internal energy for gases, we can't really cancel anything out. We can't really approximate anything. At this point, we have to consider all 4 terms: enthalpy, change in internal energy, pressure, and change in volume. And so in this scenario, unlike the solids and liquids, we can conclude that the value for enthalpy, for the change in enthalpy, does not equal to the value of the change in internal energy, much like it is for solids and liquids, right? So for solids and liquids, this is true, but for gases, this is not true. And we can see it from the equation. If you have an X amount of internal energy, to get enthalpy, you need to add your pressure times the change in volume to the term. And that'll give you the change in enthalpy. And so therefore, the numerical value for the change in enthalpy is not the same as the numerical value for the change in internal energy. All right, so what we want to do is we want to be able to calculate the change in enthalpy or change in internal energy for gases, for chemical reactions that involve gas. And so if you guys recall, we have this ideal gas law, PV equals nRT. And so what we're kind of assuming at this point is that the only way that the volume of the system is going to change is if there is a change in the number of moles of gas. We're not considering like an increase in temperature or any of that stuff that was discussed in the gas chapter in the first semester of general chemistry. Here in this case, we're simply imagining that if we have a chemical reaction that's occurring, the change in the volume of the container is dependent on the number of moles of gas or the amount of gases that is present in the system. And so once we've kind of made that assumption, we can go ahead and substitute some stuff out. So if you guys recall, the equation that relates the change in enthalpy to change of internal energy is this equation plus P times delta V. Okay. And so here, since P times delta V is equal to this term, what we're going to do is we're going to plug in this term into here. And so we're simply substituting terms out so that we get an overall equation that relates the change in enthalpy and the change in internal energy to that of the number of moles of gas, the gas constant R, and of course temperature. Okay. And so let's go ahead and understand the little pieces that's in this equation. So first of all, let's talk about the gas constant. So we know that the gas constant is 0.0821 liters atmospheres per mole Kelvin. But I want you guys to recall that both enthalpy and internal energy is expressed in either joules or kilojoules, or joules per mole or kilojoules per mole. Either way, there are energy terms. In this equation. And so that means that there must be an energy term in this gas constant. And so therefore, the gas constant that we're going to be using is 8.314, because in the units of this value, there exists the energy term joule. And so since the gas constant is joule per mole Kelvin, that means that the temperature must be converted to Kelvin. So if you guys are given degrees Fahrenheit or degrees Celsius, you must convert everything in terms of Kelvin before you can plug it into this equation. And last but not least, delta N is representing this idea of final minus initial, right? However, since N is representing moles of gas, we're trying to determine the final moles of gas, and we're going to subtract that by the initial moles of gas. And so we can go ahead and calculate, change in enthalpy or change in internal energy if we know one of these two values, and if we know the change in moles of gas, R and T. And so very similar to like a lot of algebra problems that you guys have solved in the past, you can basically solve for any one of these terms if you're given, all of those terms except for one. Okay. Now, I should say that R is always known. R is always 8.314 in this equation. And so for example, if you were given change in enthalpy, change in internal energy, and if you know the number of moles of gas, then you can go ahead and figure out what the temperature of the system is, and so forth and so forth. All right, so let's go ahead and go through an example just to see how we can use this equation. So here we have this chemical equation. If you guys notice the physical state of matter, they're all gas. And so what we want to do is determine the change in internal energy. So the change in internal energy can be translated simply as delta U. And so reading through the problem, it says that the change in enthalpy is this value. And so change in enthalpy represents delta H. And it turns out that delta H is going to be negative 450.0 kilojoules per mole. Okay. And this reaction is occurring at 33.4, or this reaction occurred at 33.4 degrees Celsius. And so if I wanted to figure out the change in internal energy, given all of this stuff, I'd probably use this equation. Okay. And so I'll go ahead and write this equation down once again. So here I have delta H is equal to delta U plus change in gas times this by R times this by T. So I'm going to go ahead and work backwards. I'm going to focus on the temperature first. So remember, the temperature must be converted into Kelvin. And so what we're going to do is we're going to simply add 273.15 to 33.4. And that value, if you plug it into the calculator, just give me a second here. So here we have 273.15 plus 33.4. That's going to equal to 306.55. So 306.55 Kelvin. And so if you want to apply, sig figs and all of that stuff, you can go ahead and round it up to 0.6. So I'm just going to go ahead and work with this raw value for now. So here we have this temperature that's in Kelvin. So we're going to go ahead and plug in 306.55 Kelvin. And that little tick mark above the first 5 just is me representing what number I'm going to cut off for sig figs. So here in this case, R, it's going to be 8.314, and the unit is joules, moles, Kelvin. It seems silly, but I really do encourage you guys to always write your unit. And if you guys don't write your unit, sometimes you might get the wrong answer because not all of the values that you inputted into the equation is in the correct unit, such that the unit itself will not cancel out. All right, so let's go ahead and talk about delta N. So moles of gas. Very similar to a previous equation that you guys use in the equilibrium chapter. The delta N, or the number of moles of gas, can be grabbed from the coefficient of your balanced chemical equation. And so, for instance, here I have 1 mole of gas, I have 2 moles of gas, and I have 1 mole of gas. And since it's delta N that we're referring to, it's definitely final minus initial. Now, if you guys are looking at it in terms of a chemical reaction, it's going to be translated as products minus reactants. And so the number of moles of gases that I have for my product is just 1. And the number of moles of reactants that I have is going to be 2 plus 1. So here I have 1 minus 2 plus 1. And so overall, my value for n is equal to negative 1. Okay. Oh, wait, hold on. Negative 2. Sorry. Okay. And so here we have an n value of negative 2 that we're going to plug into that equation. So the last thing that I want to identify are my delta U's and my delta H's. And so we're determining the change in internal energy. So this is going to be X. And here we need to plug in the value for enthalpy. And enthalpy is going to be this negative 450 kilojoules per mole. So it's negative 450.0 kilojoules per mole. And so this is going to be the instance where, you know, if you're not paying attention to your units, if you just like plug everything into the equation, kind of hope for the best, this is where you guys are going to get your answer wrong. And you guys are going to be typically off by 3 orders of magnitude. And so notice that, let me just change my highlighter here. Let's go for this orange. So this is kilojoules. And if you look at the value for R, that's in joules. So you have a discrepancy in your energy units. And so what you want to do is you want to convert one to the other. For me, it's easy for me to convert kilojoules to joules because you just multiply everything by 1,000. And so I'm going to go ahead and take this value and multiply that by 1,000. So I get negative 450,000 joules per mole. And so it allows you to convert kilojoules to joules by multiplying by 1,000, which now matches your gas constant. Okay. And so if I clean up my work, I'm just going to go ahead and make sure I have all the values and the units written out. So here I have negative 450,000 joules per mole equals to delta U, which is what I'm solving for, plus negative 2, which is the change in the number of moles, times that by 8.314 joules per mole Kelvin, times that by by temperature, which in this case is going to be 306.55 Kelvin. All right, so notice that when you multiply these two values, the kelvins will cancel out. That's really cool, right? And so what we're going to do next is we're going to just multiply out this term on the right and then just kind of simplify our answer. So I'm going to take this value and multiply it by 8.314 times that by negative 2. And so this whole term will simplify down to negative 5. Let's see here. Let's do 4 sig figs. 5.097 times 10 to the positive 3. Okay, so it's simply 5,097, negative 5,097, if you expand the scientific notation. That's going to equal to this value right here. And the unit that's left over when you multiply this whole thing is going to be joules per mole. And so since this is a subtraction sign, you're going to go ahead and add to the other side so that you can solve for delta U. And so here I'm going to have negative 450,000. And then I'm going to add that 5,097. And so the value that I get is going to be negative 4.449 times 10 to the positive 5. And my unit is going to be joules per mole. So my change in internal energy, it's going to be negative 4.449 times 10 to the positive 5. Now, if I wanted to express this in terms of kilojoules, I can go ahead and just move my decimal place 2 times to the right, 1, 2. And in doing so, I'll get negative 444.9 times 10 to the positive 3 joules per mole. And I know that a times 10 to the positive 3, or 1,000, that's the same as kilo. And so I can go ahead and reduce this to negative 444.9 kilojoules per mole. And that's going to be the change of my internal energy. Okay. And so let's think about the thermodynamic process in terms of internal energy. So when 1 mole of ethene reacts with 2 moles of hydrogen gas, it's going to go ahead and produce 1 mole of ethane. And the overall change in internal energy is going to be negative 444.9 kilojoules per mole. Okay. All right. And so once again, you guys can go ahead and use this equation to relate either enthalpy or enthalpy and internal energy, or if you're given enthalpy and internal energy, you guys might be asked to solve for the change in number of moles of gas, or you guys might be asked to determine the temperature of the system. Okay. So let's go ahead and look at another example. And this example is just a little bit more lengthy just because we have a lot more steps to work up to. And so overall, we want to determine the change in internal energy. So we're still looking for delta U. Now, instead of the problem giving us the actual enthalpy value for the reaction, it gave us the heat of formation. And so just to quickly review, heat of formation is representing how much energy was required or was released when 1 mole of that substance was formed. And so, for example, if I wanted to form water, I know that the elemental components that make up water is going to be hydrogen gas and oxygen gas. And if I wanted exactly 1 mole of water, I probably just need only half of that oxygen and 1 mole of that hydrogen. Okay. So if you guys think about it, if you take half of 2, that's only 1. Okay, so I only need 1 oxygen to produce 1 water molecule if I have 1 H2 gas. And so, there's many experiments that's been performed, doing this. And they calculated how much heat was required or was evolved when 1 mole of the product was produced from its elemental components. And so this is measuring heat of formation. You're forming exactly 1 mole. And so since you're forming exactly 1 mole, the typical unit for heat of formation is kilojoules per mole. Okay? So how much energy is required or released for every 1 mole of that substance? And so notice that our values here are given to us in kilojoules per mole. And so this little circle that is right at the top, that represents, standard state. So feel free to review some of your thermochemical notes or your notes for thermochemistry to understand standard state. And so this problem gave us the heat of formation values for all of these substances that are found in my chemical equation. And so for me to determine this value, this change in internal energy, I need some parts, right? So I'm going to just write this above. So I need to know my enthalpy, my overall enthalpy. This is obviously the term that we're looking for. And I need to know the change in the moles of gas. Value for R and value for temperature. And so looking at temperature, that one can be easily solved. So here we have 28.5 degrees Celsius. So if I add 273 and 0.15 and 28.5, that's going to give me my temperature. I know that the value for my R is always going to be 8.314 joules per mole times Kelvin. Now, the number of moles of gas is something that I can calculate by looking at my balanced chemical equation. And so if you guys are looking at, let me do this in a different color. If you guys are looking at the physical states of matter, I have liquid, gas, 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 liquid. Maybe I'll zoom in just a little bit. Okay. So I have liquid, gas, 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 and liquid. And so when you guys are working with a mixture of physical states of matter, only focus on the ones that are gaseous in state. So we're going to go ahead and ignore liquid. And so here, on the product side, we simply have the sum of these two. So 3 plus 12, that's going to be 15. So we have 15 moles of gases on the right side of this chemical equation. While on the reactant side, or the left side of the chemical equation, we only have 8 moles of gases. And so to figure out the change in delta N, it's simply going to be products minus reactants. And that's going to be 15 minus 8. And so when you guys calculate that out, that's going to be 7. So we're going to put this value, we're going to put the value of 7 into delta N. And so this is the guy that we want to find. But in the problem, it didn't give us the enthalpy of this reaction. It only gave us the heat of formation. So before we can even solve for delta U, we need to actually solve for the change in enthalpy to represent the enthalpy of the entire chemical reaction. And so you can do that by applying Hess's law. And the version of Hess's law that we're going to perform is simply the sum of the products minus the reactants. And each of the products and reactants is going to be multiplied by its coefficient. And so Let me just write it off to the side. The version of Hess's law that we're applying, and this is from first semester of general chemistry, it's going to be the sum of the number of moles times that by each of the products minus the sum of the number of moles times that by each of the reactants. So let's see how this equation plays out. All right, so what we're going to do is we're going to use these heat of formation values to determine how much energy is in each of the reactants and the products. So starting from the left, so we have this molecule, whatever this molecule is. I think it's picric acid. And so this molecule has a heat of formation value of 3,862.94. And we're just going to go ahead and write down kilojoules per mole. Now, from your knowledge of first semester of thermochemistry and the first semester of general chemistry, what is the heat of formation for oxygen gas? Now, if you guys look at the list, I didn't include the heat of formation of oxygen gas, but you should know it. And so, since O2 is a pure elemental substance, the heat of formation for any pure elemental substances is going to be 0 kilojoules per mole. Okay. So that holds true for that specific statement. And so if you guys are looking at N2 gas is another example of a pure elemental gas or a pure elemental substance. And so the heat of formation for N2 is also 0 kilojoules per mole. And so what constitutes, a pure elemental? Part of it is Hofbrinkel. So Hofbrinkel, this acronym, it's going to represent all of your diatomic gases: H2 gas, O2 gas, F2 gas, bromine gas, iodine, nitrogen gas, chlorine gas, right? And so those are examples of pure elemental gases. You can also have pure elemental substances, for example, like pure nickel. And if you were to represent like a pure metal, such as nickel, it would just be Ni and then solid or something like that. Or Ca, and it would be like solid. Or carbon, pure carbon would be carbon by itself, and it's going to have that physical state of matter, solid. Okay. So these are all examples of substances in which its heat of formation values is going to be 0. Now, if we're looking at carbon dioxide is on the list. It's negative 393.5. So this is going to be negative 393.5 kilojoules per mole. And last but not least, water in liquid form, it's going to be negative 241.83 kilojoules per mole. And so what I've done is I've just kind of organized my work so that you can see the heat of formation value that is connected to the specific substance in the balanced chemical equation. And so to apply this formula for Hess's law, what we need to do is we need to multiply each of these heat of formation values by its coefficient. And when you do that, you'll see that a specific unit cancels. So let's go ahead and look at the products real quick. So for the products, we have 3 times 0. And so when you put in 3, there's actually a unit that's attached to it. And so what is the common unit that describes a coefficient in a balanced chemical equation? It's moles. And so if we have 3 moles of nitrogen gas, and so this is representing N2, and if I multiply that by 0 kilojoules per mole, notice that the unit mole cancels. And so I'm going to go ahead and repeat the same procedure for CO2. So for CO2, I have 12 moles, because that's the coefficient, times this by 393.5, negative 393.5. And once again, notice that the unit is going to cancel out. So here we just have whatever that value is in kilojoules per mole. So last but not least, here for water, same idea. So 6 times that value. So 6 moles times that by negative 241.83. All right, so what I'm doing right now is I'm just calculating the products. So it's going to be 0, right? So 3 times 0 is 0. So I have 12 times that by negative 393.5. And then I'm going to add that to 6 times negative 241.83. And so the value for the products is going to be negative 6,172.98. And my unit is going to be kilojoules. And so if, let's see here. So let's just go ahead and round it up to the ones place. So we can do negative 6,173 kilojoules. All right. And so that's only on the product side. We have to do the same thing for the reactant side. And so for the reactant side, here we have 8 times 0. So that's 0. And that only leaves me with one calculation, really. That's going to be 2 times that value. So for the reactant side, it's going to be 2 moles times this by 3,862.94 kilojoules per mole. And so if I multiply these two, so I have 2 times 3,862.94, I'm going to get 7,725.88. This is going to be kilojoules. And so here, 2 moles, that's an exact number. And so I'm just going to keep with the correct number keep the same number of sig figs. All right, so if this is my reactants, if this is the sum of all my reactants, and this is the sum of all my products, then all I'm going to do is apply Hess's law, in which I take the difference between the two. So it's products minus reactants. And so my products, I'm just going to record the full value at this point, negative 6,172.98, then minus, okay, so please don't forget that this is a minus sign, and then the reactants is going to be 7,725.88 kilojoules. And so if I were to subtract these two, then let me see what my answer would be. 172.98. The value that I get is going to be 138988 389886. There it is. All right, so let me scoot that over. Oops. All right, so this is going to be the enthalpy of the reaction. So now that I have the enthalpy of the reaction, I can finally plug it in to my equation. And so I'm going to go ahead and just do this at the very top. So here I have the value for enthalpy was 13,898.86. And remember that this is in kilojoules. And so here in this case I have delta U, which is what I'm trying to solve for, plus here I've already mentioned that my change in moles of gas is going to be 7. Let's see here. Then I'll have 8.314 joules per mole Kelvin. And then last but not least, I'll have temperature. And so 273.15 plus 28.5, and that's going to give me 301.65 Kelvin. Yeah. All right, cool. So if you guys look at the units, notice that moles and moles will cancel, Kelvin and Kelvin will cancel, and we're just simply left with joules. But here we have a discrepancy between these two values, and so you can quickly just convert kilo into times 10 to the positive 3 joules, and that'll be your prefix conversion. And so here I have 13,898.86 times 10 to the positive 3 joules. That's equal to change in internal energy. And if I multiply everything together, so I have that 301.65 times that by 8.314 times that by 7, that's going to give me 17,555.4 267. Let me see here. So 267. And this will be joules. All right. And so the last step is to basically move this number to the other side. So I'm just going to go ahead and just duplicate this. So I'm just going to go ahead and subtract these two values. And here in this case, the change in internal energy in joules, 1.3. So here the change in internal energy is going to be 1.38813.046 times 10 to the positive 7 joules. And so let's think about sig figs. There's 4 sig figs here. And so we're just going to report 1, 2, 3, 4, all the way up to here. But since we subtracted it, then technically speaking, 5 sig figs would be the least. So we have 1, 2, 3, 4, 5. So we're gonna cut it off at the 1. So here I have change in internal energy is equal to 1.3881 times 10 to the positive 7 joules. And if I want to convert this into kilojoules, I'll go ahead and take this value. And so I'm going to separate that times 10 to the positive 7. Oh, geez. Into times 10 to the positive 4. Times this by times 10 to the positive 3. And I know that times 10 to the positive 3 is going to be a kilo, right? So then I can just tack on joules at the very end. And so what I get is 1.3881 times 10 to the positive 4 kilojoules. And then this would represent my change in internal energy for this reaction. So that's a huge change. It tells us that there's a lot of energy that's involved, a lot of energy transfer that's being involved in that chemical reaction. And so the main technique here is being able to incorporate a concept from the first semester of general chemistry, which is the application of Hess's law and heat of formation values to figure out the heat of the reaction or the change in enthalpy of the reaction. Then once you guys have figured out the change in enthalpy of the reaction, then you guys are just going to simply plug it in to the definition of enthalpy, which is relating it to the change in internal energy, and just plug in all the other stuff and solve for delta U. Okay. And so let me see here. I think I skipped a step. So not so much skipped a step, but I didn't write a unit. That's what happens if you don't write units. So the change in N is going to be per mole. So that one's gone actually. That one's gone. And so here in this case, our answer should have been in terms of kilojoules. All right, so long story short, these are 2 examples in how you guys can utilize this formula to solve for a change in internal energy. Okay. All right, so let's go ahead and talk about enthalpy and its relationship to spontaneity. First of all, let's go ahead and describe what spontaneity is, or spontaneous changes. And so spontaneous changes are changes that occur by itself with no outside assistance. And so some examples of something that's spontaneous would be the water trickling down from a waterfall, right? So there's no outside help. You know, the water just falls when it falls off the edge. We We've talked about this in the previous lecture video, which is the idea of ice cubes melting outside of the freezer on a warm to sunny day. And so another spontaneous change that occurs on a chemical level is the rusting of iron. And so if you guys take out a pure iron nail, you leave it out, over time it's going to just interact with the oxygen, producing rust. So non-spontaneous changes are changes that occur with outside assistance. And so, for example, when you guys are trying to organize your room or organize your house, I mean, the physical objects in your room and your house won't organize by itself spontaneously. I mean, that would be great if it did. But in this case, typically it's a non-spontaneous change. Building a house is another example of a non-spontaneous change. Houses just don't get built if you have wood, nails, and paint just lying around. I mean, the wood, the paint, the nails are still going to stay lying around for millions and millions of years, and a house will still not be built. Breaking down of food, whether through physical means, mastication in your mouth, or the chemical breakdown that's happening in your stomach. And so all of those are non-spontaneous changes. And so you can typically couple a non-spontaneous change with a spontaneous change. And so, for example, the energy that was released from a spontaneous change can be used to power a non-spontaneous change, and vice versa. And so non-spontaneous change can help start off a spontaneous change. For example, if you roll a boulder up a hill, that's a non-spontaneous change, but when that boulder is on top of the hill, and it can roll down by itself, which is a spontaneous action. And so an example for spontaneous events powering non-spontaneous events would be like your cell phone. So you guys typically charge your phone at night, and so the charging itself is spontaneous. It goes in the flow of electricity goes in one direction. And then the non-spontaneous change would be like the use of your phone during the day or night. And so let's go ahead and talk about relationships between enthalpy and spontaneity now that we have a better understanding of what spontaneity is, or spontaneous reactions or spontaneous changes, as well as non-spontaneous reactions, non-spontaneous changes. So exothermic reactions and spontaneity. What are, if you guys think about it, what are some common examples that would exhibit an exothermic reaction that would release heat when that chemical change occurs? And that's also spontaneous at the same time. Right, so if you guys thought about like the consumption of fuel or fuel burning, in other words, a combustion reaction. So for when a combustion reaction occurs, you have loads of energy that's being released to the surroundings. And so that is an example of an exothermic reaction. And that continuous release of energy or burning of fuel is going to be spontaneous. Another chemical reaction that is spontaneous and releases heat to the environment, in other words, it's an exothermic reaction, is the rusting of iron. And so the release of heat is actually not a apparent. And so if you guys take a nail, you guys won't get warm from, hovering around a nail rusting, an iron nail rusting. However, if you guys perform the calculations, do some type of experiment, you guys should be able to, quantitatively determine that the enthalpy value for the rusting of iron, that full chemical process, is negative delta H. And so here we see a couple of examples in which exothermic reactions could be or can be spontaneous, can lead to spontaneous reactions. So let's go ahead and look at endothermic reactions. Let's think about, chemical reactions that would require a gain of heat, but still be spontaneous. So one example that I've kind of used in the past 2 lectures is this idea of an ice cube melting. So here, if you have this ice cube, the only way for it to actually melt is if it gains heat from the surrounding. And so if the system, which is the ice cube, is gaining heat from the surrounding, then this is an endothermic reaction. And we know that ice melting is a spontaneous reaction. Another example of an endothermic reaction that is also spontaneous is the evaporation of water. And so if you have this pool of water, at some point in time, it's going to slowly evaporate on its own, right? And so this is an endothermic reaction because for it to evaporate, it must gain heat, it must gain kinetic energy for those water molecules to evaporate and become gaseous in state. And so these are a couple of examples that demonstrates that endothermic reactions can also be spontaneous. Now, there's a whole boatload of examples out there in which both exothermic and endothermic reactions are non-spontaneous. And there's also a whole boatload of examples out there in which exothermic reactions and endothermic reactions are spontaneous. And so overall, this tells us that enthalpy is only like one factor that can influence the spontaneity of a chemical reaction. And so maybe it's not exclusively the release of heat or the gain of heat that dictates whether or not a reaction is spontaneous or non-spontaneous. So we have to explore other factors that will influence whether or not a chemical reaction is spontaneous or non-spontaneous in the forward or reverse direction. And so I'm going to go ahead and leave the lecture video in suspense, and we'll pick up this concept in the next lecture video.